Swayam Prabha. Digital India. Educated India.
So this is this basically what it has done is, so apart from modeling the responsiveness of the player, it is also modeling his skill or precision at picking the best strategy and at playing the best strategy, right. So if you are again, as I said, because the sort of the main utility or the main value of this sort of theory, the way I see it, is that it's not merely as a reasoning tool, but rather as a tool for modeling when you have real data. So if you have real data of, say, players that are playing, you know, a PUBG or something like that, what is going to be the skill with which they are going to play a particular pure strategy. You want to model that based on past data. This is the sort of model that would be very useful. Okay. So this lambda models the responsiveness of the player and also models the skill or precision of the player, the precision with which he plays pure strategy. Okay. So I'll just write out now the more the general theoretical concept here. See, essentially you can build up a quantal response equilibrium using what is called a quantal response function. You can take a quantal response function, and using that you can build up a theory of quantal response. So what is a quantal response function? So quantal response function is one that satisfies the following. So it's firstly a function that takes your vector of payoffs and produces a mixed strategy. So Ri will map a vector of payoffs for player I and produce a mixed strategy for player I. Now Rij there is the jth component of that mixed strategy. Mixed strategy is going to be a vector of probabilities for each pure strategy. Rij is the probability that it gives to the jth strategy. Okay. So Rij has to firstly be greater than 0 for every j. Okay. So for every pure strategy gets some positive probability. Rij of Vi, if you look at this as a function of Vi, which means is a function of whatever you put his vector of payoffs, right? It's as a function of that, it is continuously differentiable. So it is continuously differentiable as a function of this, which means that if your payoffs change slightly, you should not have a big jump. Okay. So remember, the best response doesn't have this property. If you have two pure strategies that are equally good and one of them becomes slightly worse, then that slightly worse guy is gone from the best response. You know, it's a sudden jump. So this continuous differentiability is the smoothing that it does from where it makes some allowances for suboptimal strategies, right? That is the essential nature of a quantal response as opposed to a best response. Okay. So this has to be continuously differentiable. The other two properties are important for it to be a valid response to begin with. See, firstly, if you change Vij slightly, means if you increase Vij, if you increase Vij, the probability with which you play the jth strategy would also have to increase. So all other things kept constant, if you change Vij slightly, if you increase Vij slightly, then the probability with which you play the jth pure strategy would have to increase, right. This is another demand, naturally, because you want to play strategies that would give you high, the ones that give higher utility are being have to be played with higher probability. In fact, and the fourth one is actually saying exactly that if Vij is more than Vik, then it has to be that the probability you assign to the jth strategy is more than the probability that you assign to the kth strategy. Okay. So which means that if pure strategy J is more profitable than K, then it must get a higher probability. So, a quantal response in that sense is not anything arbitrary. Okay, it's not just some model of response with where player can do whatever he wants. There is some logic to sort of some method to the madness, in the sense that it is responsive, means that you increase the utility, the probability actually increases. If you compare two different utilities, then the one with a higher utility gets a higher probability. All of these nice properties are there in the quantal in a quantal response function. Now, what you do is you come up with these response functions which satisfy these properties. Okay, and now from here, in one step, we will be able to show that there is always a quantal response equilibrium. Okay, so what you do is you take R as R1 of V1 Rn of Vn, R of V is defined this way. Okay, so you put together these responses. Now, there is no question of it being a set or anything like that, because the responses actually tells you the exact value that the probability should, R tells you the probability with which you are going to be playing various pure strategies. Okay, so this just defines for you the mixed strategies directly. Okay. And remember, the V's themselves are functions of the probabilities. So what you have is, what you get is that these guys are themselves functions of of all these, right? So what you are, a definition, a quantal response equilibrium is a mixed strategy profile sigma star such that sigma star is a response to, so you put in sigma star to evaluate the expected utilities and compute sigma star from the response function, you should get back sigma star. You compute the response from the response function, that should be equal to sigma star. So it's precisely the fixed points type of property that we had for an Nash equilibrium, but now instead of the best response, you have the quantal response. Okay, yeah. R of V, sorry, what? Every term should? Yeah, so V1, actually I should have been careful here. What VI, actually, let me write it here. VI is VI1 till VI. I wrote Vij, right? So it's Vi this. So this is the vector of expected payoffs. From his various pure strategies. So a quantal response equilibrium is then just is a mixed strategy that is preserved under this quantal response operation. So you give a mixed strategy, compute from there a quantal response to that mixed strategy, you should get back the pure mixed strategy that you started with, and that is your quantal response equilibrium. Okay. So sigma star is a quantal response equilibrium if it is a quantal response to itself, rather than being a best response to itself. Okay. So now if you see R was defined to be continuous, right, then in that case because R was continuous, we have that, and because we have assuming finitely many pure strategies and so on, then R composed with V is actually a continuous function. So R composed with V just maps sigma to sigma, the set of mixed strategies to set of mixed strategies. Yeah, is a mixed strategy profile. It is Ri is already taken to be having image here. It is already a mixed strategy. Ri is belongs to sigma. Okay, so this is a map from here to here. It is continuous, and sigma is closed, convex, and compact, closed, convex, and bounded. So then again from Brouwer, just like we did today in the start of the class, Brouwer's fixed point theorem implies that there exists a quantal response equilibrium for each quantal response function. So you can see there is a little too much flexibility if you see, because you can define whatever quantal response function you want and you will get a quantal response equilibrium. Okay. Now this too much flexibility is good again when you are dealing with data. Sometimes you get erratic data and no matter how much you try, you will not be able to fit the very demanding theory of games to it. But so this kind of a softer model like this can fit in your data. Okay. So I'll end with one more example of a response function. So you can do the following. You can consider any CDF like this. Okay, consider a CDF. This is a cumulative distribution function. This is a CDF. Okay. And I am going to assume that this has some sort of a symmetry property. So f of x, okay, should be equal to 1 minus f of minus x, which means that if you look at something like this, so because this is a CDF, it means that it eventually, as x tends to plus infinity, you are going to get, this is going to tend to 1, and x tends to minus infinity, it is going to tend to 0. Okay. That's your f. Now, when I write this symmetry property, what this basically is saying is that I should be able to, if I take an x like this here, this height here is fx. If I take the mirror image of this, here this x, which is minus x, and I look at this height is 1 minus f of minus x, right. So then in that, what it's basically saying is that this shaded height is equal to this shaded height. Okay, so there's a sort of a flip and a rotation around that sort of symmetry is being assumed. Okay. Now, if you take any such function, then what you can do is, I'll write this for our matching pennies game. You can write out a quantal response in this kind of form. You can take sigma I1 to be f of lambda ui1 minus ui2. Okay. So player I plays his strategy 1 with this probability f of this. Okay. Now, in particular, you can take fx to be 1 by 1 plus e raised to minus x. And this is something that all of you would have seen sometime or the other if you have done some machine learning. This is what would give you logistic regression, right. So what you get from here is you get a logit response, quantal response generated by the logit function, okay, which is, and it looks like something like this. You get e raised to minus lambda x so that so the exponential, whenever it comes up, many interesting things come up. It's the it is part of the partition function. So you can now, it turns out unfortunately because of the nature of this, we can't solve for these sigmas in closed form, but you can we can try to plot them, and I'll just show you what's interesting is how they tend to look. So I have I can just draw this quickly and show you. So on the left, on the x-axis, I have the probability that the column player plays H, and on the right y-axis, I have the probability that row plays H. Okay. So if this is 1 and this is being plotted for x equal to 1 by 10. Okay. So if x is equal to 1 by 10, this column guy plays H, remember, with probability 1 by x plus 1. So so this becomes, this is almost equal, very close to 1. So and the row player plays H with probability half. So this dot here is your Nash equilibrium. Okay, this is 1 by x plus 1. Now you can also do plot the logit response or the quantal response to of each player as a function of the other guy's strategy. So I can plot, for example, the logit response of the row player as a function of the player as a function of what the column player is playing. So I take the column player's so this as the independent variable and plot the row player strategy. So it turns out it's something that it actually passes through the Nash equilibrium and it has this sort of form. So this is the logit response of row player. To column player strategy, column players. And I can similarly plot the logit response of the column player to the row player strategy. And the place where they intersect is your quantal response or logit response equilibrium. Okay, so here now I am taking the domain of this one is going to be this. This is the domain. The vertical axis is the domain for the green line. The horizontal axis is the domain for the red line. Okay, and wherever they intersect, this is now your logit QRE. And it is distinct for, it turns out to be distinct from the Nash equilibrium. People have tried to fit in data and all that into this, and they found that the data seems to be somewhere here. Okay, now it's anybody's guess about whether this is whether it's closer to Nash or closer to logit. But but the interesting thing is what happens as x changes. So as x changes, this figure changes quite a bit. I'll just quickly draw that as well. As x, when x, if you change x from 1 by 10 to say 9, okay, so then in that case, then firstly the Nash equilibrium shifts here. So the Nash equilibrium will shifts because the one coordinate remains at 0.5, but the other coordinate has shifted. So this becomes the new Nash equilibrium, and these red and green curves actually shift, end up behaving something like this. This becomes the red curve, and the green curve becomes something like this. And this point here is your new logit QRE. Okay, so the good thing is, because there is this, so one of the dilemmas that we have when we think about games from the point of view of data sciences, right, is that how do we interpret past data? Okay, is the past data something that is that only an exploration by the players, just some trial and error trying to know what the strategies are, what the opponent's capabilities are, what might the opponent be interested in, etc. Is it just pure, what we call exploration in reinforcement learning and so on? Is it just that, or is the past data already having a strategic intent built into it? So, has the past data been arrived at with players playing with strategic knowledge and with strategic intent and strategic emphasis? So, all these strategies that they have played in the past is not exploratory only, it is actually intended as a strategic move by the players. Okay. So, if you interpret the past data in one way, if you think of it as pure exploration, then the opponent actually doesn't come into the picture. The opponent is just there as noise effectively. Whereas, if you think of the past data as being strategic, right, then the past data itself represents a game, and what you are seeing over there is the outcome of the game. And so, therefore, you don't know what the players could have otherwise done. You do not know the space of the game outside of what has actually come out as the outcome. So, what the quantal response actually, in my view, what its main sort of benefit that I have found in my own work and so on is that it gives you this kind of a soft in between model that is partly exploratory, sort of models a little bit of imprecision, lack of skill or lack of experience on part of the players, because by bringing in that factor lambda and so on, and at the same time it has some intrinsic merit as a solution idea. So, it's not completely non-strategic either. So, because if it is in between like this, it gives you an opportunity to model this the game from its previous data, from whatever you have seen players have done previously. Okay, so that's one of its utilities. Whenever you want to do any modeling exercise from data, this is one direction to go.